I'm going to share my screen with you. It's going to be this one. Okay, so are we as content as we could be with the equilibrium maths? I'll have a look at them now later today, but we'll make the assumption that everyone's okay. Nobody got in touch. So Lucy, I have seen yours. I got distracted with what I was doing, so it's on my list. So we're going to look at now what's called acid equilibria. So there's a little bit of revision first. So the question that is here on the screen is specifically for higher levels. So we have a thing called the ionic product of water, and we have self-dissociation of water and pH. So you got to see, can we get our heads a little bit around those? Can you remember things about Arrhenius? So you might have to turn on mics now to tell me weird and wonderful. So we did Arrhenius and we did Bronsted-Lowry last year. Can you remember anything? What's Arrhenius's definition for an acid?
Things that dissociates fully or something.
So an acid dissociates. What does it dissociate to produce? It dissociates in what?
In water to form OH.
Yeah. So if it's water, if an acid dissociates, is water H plus or OH? H plus. So Dan, you're writing this now with us. So an acid is a substance that dissociates in water to produce H plus ions. What would be the corresponding definition for a base?
Produce OH minus.
Produce OH minus. So there was a word if you were to give away one proton. Can you remember? And there was another.
Proton donor.
It is, so proton donor is Bronsted-Lowry, but if you give away one proton as opposed to 2 protons as opposed to 3 protons, there was a word that we had.
Conjugate acid base pair.
Correct. You're not incorrect, because they differ by 1 proton, but we had this word. Do you remember this word? I think it was monoproteic and monobasic might have been the word we used. So yeah. HCl is monobasic because it only, when it dissociates, it's only going to dissociate into one H plus and a Cl minus. Whereas if you have 2, you're now dibasic or diprotic. So something like H2SO4, when that dissociates, it's going to give you 2H plus SO4 2 minus. And then you have tribasics, which are H3PO4. So when that dissociates, that gives you 3H plus PO4 3 minus. So using Arrhenius, strong acids, strong bases, how are you going to describe them?
They dissociate fully in water.
Yeah, so strong is the ones that dissociate fully, and weak only do not fully dissociate or only slightly dissociates. So remember now, there is one word we can't use, which we can't say. So you have a choice of do not fully or slightly dissociate. So Arrhenius is not a true representation of acids, because not all acids need to be dissolved in water to show their properties. So that's why then Bronsted-Lowry's definitions became better. Are we okay to flick? I'll take silence as a yes unless somebody shouts. So then we had Bronsted-Lowry. So what was his definition for an acid or a base, or their definition? So Roisin, I think it was you said it, or maybe it was Izzy.
Oh, wait, I'm not done finishing the past slide.
There you go.
Is an acid a proton donor?
An acid is a proton donor, and what is a base then?
Proton acceptor.
Proton acceptor. So Bronsted-Lowry is a better definition because water doesn't have to be involved. You don't have to dissolve things in water. So that's why Bronsted-Lowry would be used, and would be used more, I can't pronounce the word now, preferentially, I think is the word. All right, Dan, you let us know when you're ready. Need to make my list. I presume, Dan, you're happy? Thumbs up? Because Dan, we can't hear you talking.
Do I write down the donate 1 ions, 2 ions, 3 ions thing?
No, you
Where
can.
write-
You don't have to. You just need your definitions. You just need these top two
Okay.
and these bottom two. Can I go move on? Oh, he's still writing. Okay, Dan, happy to go? So you're still on mute, dude.
Oh, I think I've memorized those.
Okay, but we know we're on page 140 in your pink book. Yeah, so you're just filling in the gaps. So for Branstad,
In your pink book?
yeah, and
I'm doing it just in... I'm just doing it on a regular refill
no,
pad.
so I was wondering I was taking you so long. So pink book, page 140 of your pink book. Or at least it's 140 on me. So that'll save you some time. So you've told me that Branstad-Lowry, an acid is a proton donor, a base is a proton acceptor. Can you remember the word for something that can act as both an acid and a base? So water is this thing. Because it can donate protons and it can accept them. Oh, I can see thinking on my screen.
Do I have to?
You definitely need this and this. We'll put you out of your misery. So the word that we had was amphoteric. So water is your example for this because water can both donate and accept protons. So the good thing about Branstad-Lowry is that you don't have to dissolve things in water to decide whether they're acids or bases. And here we have this question. An acid turns into its conjugate base when? What does it have to do with the proton? Lose it or gain it?
Lose it.
Okay, and then similarly a base turns into its conjugate acid when it gains a proton. So we would have done a number of these reactions. So my silly sentence is all boys sing well. An acid and a base gives you a salt and water. Can you remember what we said neutralization actually is? There is a formula that shows neutralization on the basis of acid stroke base. And you remember what that was? So while this is a neutralization reaction, it's not actually highlighting directly what things are responsible for neutralization. So I'll give you a hint. Tell me what's the neutral thing in this equation?
Water.
Water. So how do I make water from an acid and a base? Or what part of the acid, what part of the base actually makes the water?
The H plus and the OH minus.
Yeah, okay. So that is your... Ooh, it's not going to go. It's going to do it backwards. So H plus from your acid and your OH minus from your base, that when they combine together, that is neutralization because you've neutralized the acid portion, you've neutralized the base portion, and you've made neutral water. And then just the last part of this is Branstad-Lowry's definition of a strong acid is something that's a good proton donor, a weak acid is a poor proton donor, and vice versa for
Bases?
Thank you, Dan, for bases. So bases will be good proton acceptors or poor proton acceptors if they're weak or strong. So that is fifth year revision now in 10 minutes. So we happy to move? Dan, you good?
I think I still need a bit of time.
Alrighty.
Thank you.
You are very welcome. So I would just make the point that even in Arrhenius, when we talk about H pluses, in reality, we're talking about H plus H2O. So remember we had this, the hydronium ion. That is a more correct way to represent H pluses. But in Arrhenius, we just use the H plus. So this is one of the limitations of Arrhenius. So in Arrhenius, you have to have an aqueous solution, and technically it is hydronium rather than H plus.
You can move on now. I got the gist.
Thank you so much. So Dan, you're only going to do the top of this page. I will the first kind of 2 parts to it, and then you don't have to write anymore. So for acids and bases, we do a thing called the ionic product of water. That is higher level. We do a little bit on calculating.
Do I write this down?
Say it again.
Where do I write this down?
No, so this is just an FYI, and then I'll tell you what you're doing. So this is what we're doing. So the ionic product of water, that portion of it is going to be higher level. We have to calculate pH and work out concentration of hydrogen ions. And there's both higher level and ordinary level in this. And then the last bit that we do is we actually look a little bit more at what happens when we do our acid-base titration. So we draw what are called titration curves, and hopefully then from those it'll make sense to you why we pick the indicators that we do. But again, this is higher level. So half of this is higher level and half of it is ordinary. So we have it's called the self-dissociation of water. So water is going to dissociate to a small extent, and this is what it looks like. So it gets a reversible reaction symbol because it can go both ways. So that's going to go in the top of page 141. So this is the equation for the self-dissociation of water. So we're now going to manipulate this a little bit to turn it into something else. So everybody in the audience should be able to write a Kc equation for that value. And Dan, that will be the last thing that you have to do. So you're going to write the Kc for this.
Do I do that now?
Yeah, you do that, and then you don't have to write for a little while.
Where do I write this exactly?
So if you read the top of page 141 in the grayed out box, this is the grayed out box. And underneath it says write the Kc expression for this equation. So you should have had some practice on Kc. So lads, anyone want to tell me what your Kc is?
H plus by OH minus over H2O.
Perfect. Okay. So Dan, you can now just have a rest for the rest of this page, and then we'll
Do I write all this KC stuff?
see where it says at the top of page 141, write the Kc expression for this equation.
It says for this reason pH is defined as.
It's
Okay.
140 for us, I think.
Okay, 144 on you. Thank you,
140,
Cam.
140.
140, Cam. Or thank you, Cam. So 140, Dan, you have a space.
Got it.
Okay, so you can now have a rest while we figure out the rest of it. So the rest of this now is just a little bit of manipulation. So from that Kc, because water is a constant, what they do is so this is your Kc. Because water is a constant, they rearrange it to move water to the left-hand side. Because Kc is a constant, and now our water concentration is a constant. And once you've done this rearrangement, they now name this Kw. So Kw is really Kc, your Kc constant by your concentration of water constant, and you can calculate it from a hydrogen ion concentration and a hydroxyl ion concentration. So it's called the ionic product of water, Kw. So they would ask you to show how you would get the ionic product of water, and you start with the H2O going to H plus OH minus, and then you'd write your Kc, and then you'd shove your water over to the left hand side, and now your Kw is equal to H plus and OH minus. So this is the self-dissociation of water, and this is your Kw, your ionic product of water. So there is a number for this, and that number will have significance in a minute. So you have the gap for it. It says Kw is the ionic product of water, and at 25 degrees it is 1 by 10 to the minus 14. So can you remember when we did Kc, what things would change your Kc concentration? Remember, we did all the equilibrium scenarios. So if you change the pressure, that doesn't have an effect on Kc. If you change the concentration, that doesn't have an effect on Kc because of Le Chatelier. It's going to shift to minimize. So it is temperature. So Kw is going to be similarly affected by temperature. So if you increase your temperature, you're going to increase your Kw. So that's just a point, and it's like a random question they can answer. So Kc is affected by temperature. Kw is also, affected by temperature. So then we kind of do, it's like a little bit of a derivation. So we have to take this equation here, and we're going to now jimmy it around a little bit. So if you just want to highlight for yourself, this is like Kc in that it's affected by temperature. Are we happy to click to the next slide?
Miss, you know what it says? As you increase temperature.
So as you increase temperature, Kw increases.
Okay, thanks.
Thanks, Sam. Alrighty, and this is just showing you, if you were to have your Kws increasing your temperature, this number here is getting bigger. So it is temperature dependent. So here's the information that we have now. So Kw is equal to your hydrogen ion concentration by your hydroxyl ion concentration, and that is equal to 1 by 10 to the minus 14. But these two guys here are the exact same concentration. So what they do is, and that is in your maths tables, what they do is H plus is essentially equal to OH minus. So you can rewrite your Kw like this. So instead of having the H plus and the OH minus, we now have H plus squared because they're the same thing. So if I wanted to find H plus, what would I do to this number?
Square root.
Yeah, so if to find H plus, I square root it. If I do that piece of maths, hydrogen ion concentration is 1 by 10 to the minus 7. So for a neutral solution, your hydrogen ion concentration and your OH minus concentration will be equal to 1 by 10 to the 7. And you'll see how this is significant in a second in terms of relating it to pH. So obviously that is a square root. So that little page on page 141, they can ask you to do kind of that, is derivation the right word? So you start off with your formula for H2O, you turn it into a Kc, turn it into a Kw, recognize that your H plus and your OH minus are the same, so you can find out your hydrogen ion concentration or your OH minus concentration. I'm not sure if I'm using the right word. All right, Dan, you're going to be back with us. Content with that? Thank you.
You know, the way it says in the maths tables.
Yeah. So if you wanted to know what the ionic product of water is, that number is in the maths tables. I don't have maths tables at home now, so I can't find it for you. But
Just the 1 times 10 to the power of minus
14. Yeah.
Okay.
Once we look at pH, you will remember this number. That will come to you. So it's on page 141 now that we're looking for. So Dan, you are back with us.
Yes, I know.
Yes, you are. So pH, the definition for pH is actually a formula, and this is your formula. So on the top of page 141, the definition of pH is minus log to the base 10 of your hydrogen ion concentration, is how you say it in words. This is acceptable for the SEC. So the SEC will, if they ask you to define pH, that's what they're looking for. You are going to have to use this formula in a piece of maths. So it's really important that you recognize that the hydrogen ion concentration is in big M. So sometimes they might give you grams per 100 centimeters cubed, and you have to bump that up to turn it into moles and then turn it into moles per litre. And if you were to say it in words, which you don't have to do, it is negative log to the base 10 of your hydrogen ion concentration. So we're going to use this now to work out pHs of strong acids, and we even use it indirectly in strong bases. So negative log to the base 10 of your hydrogen ion concentration. Okay, I'm assuming everyone is happy. So this is, you have a version of this pH scale on your book. So once upon a time when we were measuring pH, we were measuring it, we thought, oh, we're measuring strength of an acid. Well, actually we're not. We're measuring how many protons are present, how many H pluses are present. So you have, it's this part. Talk to me.
That's kind of interesting.
It is. So if you're a very strong acid, you have bucket loads of protons. If you are a weak acid, you don't have that many protons in solution. And pH is influenced by temperature. I don't know, is this going to animate wrong? It is going to animate wrong, isn't it? Yeah. So pH is temperature dependent. But this time, if you increase your temperature, you end up with a decrease in your pH. So pH is temperature dependent. As you increase temperature, pH decreases. There are limitations to the pH scale. So we totally ignore them in school in terms of, for some of them, or even if you go into undergrad labs in university. So you can only measure the pH of something that is dilute, and it has to be at 25 degrees Celsius. pH scale only works on an aqueous solution, so you have to have water present. As far as we're concerned, the limit is 0 to 14. So you can actually have negative pHs. That is a possibility once you get to university. And if the concentration is too low, you can't actually get a read of a pH. So you can pick any two of these that apply. So technically this first sentence is actually 2 marking points.
Oh, I just realized I forgot what the definition of pH was in words. Forgot to write that down.
Okay, so pH in words is, ooh, apologies. Lads. So pH in words is negative log to the base 10 of the hydrogen ion concentration. You will never have to put it in words. This is totally acceptable as far as the SEC are concerned. They don't care. That is their definition for pH, and that is also the piece of maths you use for some of the calculations. So
Wait, does that mean the grayish ones are higher level thing?
no, it's just important to know that pH is temperature dependent, and that pH scale is actually more interested in concentration of hydrogen ions, rather than strength. How do I measure pH in a lab?
Universal indicator.
It would be one. What would be the other method? I have some of them in the lab, but they don't work. Do any of you do your work experience in biology labs? No? Is it okay to flip off this? So Dan, thumbs up because I can see your face. Thumbs up or thumbs down? Okay. So universal indicator is one of the ways. So the other thing that you can use is a thing called a pH meter or pH probe. So this is an electronic version of measuring your pH. So you put your probe in and it detects the hydrogen ions that are in there and converts it to a number. So we'll just wait for that.
So what does that say beside the first limitation of the pH scale?
So this
Is
one, this part here.
Yeah.
Yeah.
The
So you just technically need to remember 2 of the limitations, and that one sentence is 2 limitations.
Oh, okay.
So it's 2 marking points on a scheme. I'm just trying to see. It's gonna have to cover our movie for 1 second. Come on. Here we go. Okay, the assignments now is gone to ridiculously slow. Teams is on a go slow for me. So there is something that is going to ping. It's moot because we haven't gotten that far yet. So you cannot do it. So there's going to be, I'll see, can I cancel it? I don't want to delete it. I'm going to just update it. Where did you go? No, okay. So there is a thing that's going to ping if I don't get to it. You just have to ignore because we haven't gone far enough. So look, we'll let it there now. When do we see each other next? You have your assessment tomorrow is going to ping. I think it pings at 8:40 in the morning. I've told you how long you have to do it, and I just want it back by 4 o'clock in the afternoon. Is that okay? And I see you again then on Friday. So we'll see everyone on Friday, and we'll see where we go with our maths.
I believe I'm done with that slide.
Okay, well, we are done. So there, you have your assessment tomorrow. So I'm going to stop my share now. Is that okay with everyone?
We're done with everything right now.
So we're done with today. We're done with this.